Welcome to the video-based overview of APTI 419B, Preparation of Fine Particle Emissions Inventories. 419B is a two-day course developed for classroom presentation and discussion. This is the first of several video-based modules that collectively provide an overview of the full 419B course. I encourage you to participate in the 419B course if you need a more in-depth understanding of PM 2.5 emission inventories. This module, Introduction to PM 2.5, discusses PM 2.5's nature and sources. In this introduction to PM 2.5, we'll discuss what are fine particles and why are they important. You'll see that not all fine particles are the same. In fact, they're really a complex mixture of different compositions and from different sources. Some particles are directly emitted and some form in the air from gases. This formation is affected by atmospheric conditions and the amounts and types of gases available. Because PM 2.5 is a complex mixture, particle composition varies regionally and even within local areas. Fine particles are those particles smaller than 2.5 micrometers aerodynamic diameter. What's so important about fine particles? Well, their health implications. Fine particles aggravate respiratory problems, especially for children and elderly, and they can cause irregular heartbeats and even premature deaths in heart and lung disease patients. There's a national ambient air quality standard for PM 2.5, and there's emerging concern for even smaller particles. Visibility is reduced by fine particles, and fine particles degrade scenic vistas. Water quality is also an issue because fine particles deposit onto surface water and onto the ground. They can leach into the groundwater and alter acidity and nutrients. Material damage is another concern since fine particles corrode and stain buildings and landmarks. Also, fine particles have recently been implicated in climate change because they scatter and absorb light. There is such a broad range of impacts because fine particles are a mixture of several particle types and composition. The major types of fine particles include carbonaceous matter, crustal matter, ammonium sulfates, and ammonium nitrate. Also, there are other types of fine particles that comprise a minor part of PM 2.5 in the air. Some of these would be biological materials and some man-made particles. Let's discuss this mixture of particle types in more detail. It's a complex mixture that includes both particles that are directly emitted from sources, we call those primary particles, and those particles formed in the atmosphere from precursor gases, we call those secondary particles. The primary particles are on the left side of this slide, represented by the black, brown, and white symbols. The secondary particles are on the right side of the slide, shown in gray, yellow, and red symbols. Their precursor gases are also shown. Let's look more closely at primary particles. They include crustal matter, elemental carbon, abbreviated EC, organic carbon matter, abbreviated OCM, and other particle types that also play a minor role. Primary particles are from both incomplete combustion and from the Earth's crust. Let's start with elemental carbon. It's also known as black carbon, and it's always a primary particle. Elemental carbon is a byproduct of incomplete combustion. These same combustion sources also emit organic carbon matter. Some organic carbon matter is primary, but we'll see later that some is also secondary. The other major type of primary particle is crustal matter. These are mainly oxides and carbonates found in the Earth's crust. Examples of common crustal compounds include calcium carbonate, iron oxides, silicon dioxide, also known as sand, and fly ash. Most crustal material is fugitive dust. Fugitive dust is crustal matter emitted into the air at ground level directly from open sources and not through a stack or a vent. Most crustal matter in the air is larger than PM 2.5, but the largest particles settle out quickly. Now we'll discuss secondary particles. They include ammonium sulfate, formed from SO2 and ammonia gases, and ammonium nitrate, formed from NOx and ammonia gases. So ammonia gas is a precursor to both sulfate and nitrate. Now we recall that we said that some of the organic carbon matter is directly emitted into the air, but much of it is also secondary, formed in the air from volatile organic compounds. Let's talk a bit more about sulfate and nitrate. Sulfate is mainly found in its fully neutralized form, ammonium sulfate. But if there's not enough ammonia available, it can be found partially neutralized as ammonium bisulfate. It's also found as sulfuric acid mist or droplets. Nitrate is formed from NOx and ammonia and is found as ammonium nitrate. What if there is not enough ammonia to react with all of the available SO2 and NOx? If SO2 and NOx are competing for the ammonia will react first with the SO2. We've said that organic carbon may be found in either primary or secondary particles. But these particles aren't pure carbon. Each molecule of organic carbon also includes associated elements, mainly oxygen and hydrogen. They add to the mass of the particles. We call this extra mass the non-carbon organic matter, or NCOM. The amount of mass it adds depends on the type of source, but NCOM can more than double the particle mass of OC for some source types. Let's recap what we've learned about PM2.5 composition. Primary particles are directly emitted. They include crustal matter. These are mainly oxides and carbonates commonly found in the Earth's crust. Crustal matter is mostly larger than PM2.5. Elemental carbon and organic carbon matter are the other two main types of primary particles. Secondary particles are formed in the air from precursor gases. Sulfate is found in the air as fully neutralized ammonium sulfate, partially neutralized ammonium bisulfate, or as H2SO4 sulfuric acid. Nitrate is most commonly found as ammonium nitrate. Organic carbon matter can be either primary or secondary and includes associated hydrogen and oxygen. Now, let's see how the amounts of these PM2.5 components vary across the U.S. For example, in the Northwest, sulfate is low, but organic carbon is high and there is some nitrate. In the Midwest, we see much more sulfate, a little less organic carbon, and a bit more nitrate. In the Southeast, the sulfate is similar to what we see in the Midwest, but there's almost no nitrate in the Southeast. Some urban areas have different mixes of particle types, but there is much similarity east of the Mississippi. High sulfate and high organics prevail. Source types, emission rates, and meteorology all play a role in determining the composition of PM2.5 in the air. In addition to regional and local differences, we also see differences in the composition between an urban area and its surrounding region. Mostly, these urban regional differences are seen in carbon and nitrates. Differences in crustal materials can also occur, but not sulfates. Sulfates are relatively constant across large areas. When we see higher concentrations of carbon or nitrates or crustal in an urban area than in the surrounding areas, we call it urban excess. Urban excess serves as one indication of the type of control strategies that might work in a particular urban area. The next slide illustrates the urban excess concept in Atlanta. Please look at the leftmost column. The entire column height, including both the yellow and orange, represents the average sulfate in the Atlanta urban area. The yellow part of the column shows the annual average of sulfate in rural sites surrounding Atlanta, seen as the blue dots on the inset map. The orange represents the excess sulfate found just in the Atlanta urban area. In the Atlanta area, nearly all sulfate is associated with the regional contributions from outlying sources. There is virtually no sulfate urban excess, but the nitrate and carbon concentrations are nearly double in the Atlanta urban area as compared to the surrounding areas. This is a significant urban excess. Of course, urban excess isn't the same everywhere. The urban excess in an area can point to the need for inventory improvements or to potential control strategies. This summarizes the larger source categories of PM2.5 direct and precursor emissions. It shows that combustion is a major source of both directly emitted particles and precursor gases. Now let's take a quick look at the National Emission Inventory for PM2.5 and its precursors. The main source categories for each pollutant are highlighted in red. Nationally, in 2005, direct PM2.5 emissions are about 5.5 million tons a year. Precursor gas emissions total 10 times that much. But remember, only a fraction of the precursor gas emissions are actually converted into particles. Electric utilities and industrial boilers are key sources of NOx and SO2. Mobile sources emit more NOx than utility boilers and also emit VOC. VOC is also emitted by solvent evaporation and miscellaneous sources. This miscellaneous category is very important for PM 2.5, VOC, and ammonia. What are these miscellaneous sources? Well, for PM, it's fugitive dust and biomass fires. For ammonia, it's animal waste and fertilizer. For VOC, it's biomass fires. What source types contribute in your area? A good inventory can help answer that question. We've covered a lot in a short period of time, so let's stop and review. We've seen that PM 2.5 is a complex mixture of both primary and secondary particles. The concentration of PM 2.5 in the air is usually dominated by organic carbon matter and sulfates. There are differences in PM 2.5 composition across the U.S. and between urban and non-urban areas. There is often an excess of organic carbon matter in urban areas due to mobile sources. The main source of primary 2.5 and its secondary precursors in an urban area is usually combustion. The full APTI 419B course contains more detail and examples. It also adds a few new subjects. For example, it discusses the uses of composition information and how to develop speciated PM 2.5 inventories. The full course discusses ways to relate sources to PM 2.5 in the ambient air, and it also discusses day-to-day variations and spatial patterns of emissions. Thank you for your interest in PM 2.5.